These are the frequently asked videos for Algebra 2, Section 52D2, and we're going to start with number 35, which says find the relative maximum and relative minimum of the graph of each function. Well, in order for us to find that max and min, we're showing you how to do that on your graphing calculator. So what you want to do is grab your graphing calculator and go ahead and punch this function into the y equals category here. So y equals, and then we go ahead and put in number 35, which is x to the third. So x caret symbol 3, and then I have to bring that down to do the next term. There we go. And then we have plus 4x squared. And minus 5x. All right, now what I'm going to do is I'm going to hit zoom 6 to get that nice negative 10 to 10 window. We might not see what we need there, but we very well might. So now I notice there's a portion of this graph that I need right up there, because that would be a relative maximum. So what I'm going to have to do is I'm going to have to change my window so that I can go up higher. And to go up higher, we need to see more of the y's. So window, and I come down to y max, and I could try doubling it. I'm going to try 25. I'm going to take 150% of what was on there before. Now I hit graph. And now I can see both the relative maximum and the relative minimum. So I hit second trace, and I want to do that maximum first. So I'm going to hit number 4. And then Blinky shows up, and I have to use my left arrow to get Blinky to be to the left of the hill and press enter. And then my right arrow to get Blinky to go to the right side of the hill and press enter. And enter through guess. So my answer for this one would be about negative 3.2 and about 24.2 for the relative maximum, also called the local maximum. And then I have to hit second trace and number 3, because I have a valley down here by the origin. So I hit Blinky there until I can get Blinky on the left side of that valley and press enter. And then move Blinky to the right side of the valley and press enter and enter through guess. And that one I would write down that it is about 0.5, negative 1.4 for the coordinates of that one. And that would be a relative minimum. Remember, hills are maximums, valleys are minimums. So that's what we would use the calculator for these relative maximum and relative minimums of anything that's bigger than a quadratic in degree, which would be our cubics, etc. Then, number 39 starts, there's some word problems in this particular on this page that all deal with the same type of situation. So number 39 says, we've got some metal work. A metal worker wants to make an open box from a sheet of metal by cutting equal squares from each corner as shown. Write expressions for the length, the width, and the height of the open box. All right, so it was 16 inches, but now on each one of those sides, they're going to cut out an X. Notice all of these would have the dimensions of x and x. So we'd have 1, 2 of those being cut out. Same thing with the 12. It was 12, but now they're going to have to go ahead and cut out 2 x's in order to get it to fit. And once they fold these little flaps up, notice those will always be x units high. So those are the expressions for the length, width, and height of the open box. And then B says, use your expression to write a function for the volume of a box. So, volume of x, the box that we have there, and I would just put the x in the front, because it's kind of awkward when it's hanging out in the back like it is, but it wouldn't be wrong. We could just copy the same thing down. And then C says go ahead and graph the function and find the maximum volume of the box and the side length of the cutout squares that generate this volume. So at this point, you don't have to multiply it out. You could just go ahead and put it into the calculator just as it is, and the calculator would give you back a graph that you could use to find the maximum, and then put those values back into what we have here. So that's what I want to do, is get back to my calculator here and go to y equals, clear out what we had before, and now this time we had an x, parentheses, 16 minus 2x, parentheses, parentheses, and 12 minus 2x, parentheses. So it's all in there, and I'm going to try Zoom Standard. Probably isn't going to work. This is a word problem here. So yeah, we see kind of a goofy little view of what's going on there. So we'll go to the window and realize that we're talking about dimensions of a box. So 0 is going to be the smallest dimension that we could have. And the box itself had dimensions of 12 by 16. So obviously, we can't go much bigger than that for the x value. So I'm going to try 18. Actually, we can't go any bigger than that. And then I will go down to the y min and also make that 0. And then the y max. The y is the volume piece. So you think about what 12 times 16 would be, and actually I'll just put 160 in there, thinking about something a little bit easier to try to figure out what that maximum would be, since those were the initial dimensions. So now I see I'm just missing on the y here, that maximum. So I can go ahead and now make a better educated guess at what I can put in for y, because I need those y's to be a little bit higher. So let me try 220 just to make sure that I can see it, and hit graph. And there it is. So now what I want to do is, again, they wanted me to tell them the maximum volume of the box and the side lengths of the cutout squares that generate that volume. So I want an x and a y at the max, which is exactly what second trace does when we're finding the maximum value. Now, unfortunately, Blinky's way too far over to the right, so I've got to hit my left arrow a lot to get Blinky back over here where I can find that relative max. All right, so now he's on the left side of the hill, and I press enter. Right side of the hill, press enter, enter through guess. And that means about 2.3 would give us a maximized volume of 194. So that would be what we would want to write down for this one, that the volume would be about 194 cubic inches and about 2.3 for the dimension. So again, 194 cubic inches, and then we had, like I said, about 2.3 inches for the x value there. So that will do it. And they did want you to graph it, so at least make a sketch of what you saw when you had that on your graphing calculator. All right, then 40, 41, and 42 are asking us to go ahead and write the functions in factored form and then check by multiplication. Well, I'm not going to bore you with the checking by multiplication, but pretty obviously there's way too many x's in this one, and 3 can be pulled out of all of them. So x is the highest power that I could take out, x to the first, and then the 3 will come out as well. So I would need an x squared to get 3x to the third back, and then need a negative 9x if I multiplied that together to get the negative 27x squared. And then I would need a plus 8 to get that 24. So far I have factored out a common monomial, but chances are pretty good that I can continue on and keep factoring if I can find two numbers that multiply to positive 8 and add to negative 9. And that would be negative 1 and negative 8 that would do that. So that is the factored form for number 40. For number 41, again, you notice there seem to be way too many x's, and we never leave that negative in front. And so we're going to pull a -2 and an x out of that, because when we're factoring in a binomial or a trinomial or binomial situation, we always want that first term to be positive when we're factoring. So what we need here is an x squared to get back to the -2x to the third, and then we need a plus x to get us that -2x squared in the middle, and then we would need a -20 to get us that positive 40x in the back. So now I want to factor. There's no perfect squares here. I want to factor using two numbers that multiply to -20 and add to 1, and that's going to be +5 and -4. So going back to the old factoring that we were doing in one of the previous chapters. Then the last one, hopefully you see that there is an x squared that can come out of this. So this would give us x squared times x squared plus 3x minus 4. And the x squared would just stay out in front. And then we need to find two numbers that multiply to -4 and add to 3. That would be +4 and -1 that would do that. So those are in their factored form. And again, what that tells us is where the zeros are going to be graphically, which is really, really helpful when we're graphing. Then this one, a lot like, volume problem we were talking about before, it says a storage company needs to design a new storage box that has twice the volume of its largest box. Its largest box is 5 feet long, 4 feet wide, and 3 feet high. So the first thing I'm thinking is, if I have to find something that's going to be twice that volume, I need to know what that volume was. So we take 5 times 4, which is 20, times 3, which is 60 cubic feet. And they want their volume of their largest box to be twice that. So 2 times that 60 cubic feet is going to give us 120 cubic feet. And this says the new box must be formed by increasing each dimension by the same amount. Find the increase in each dimension. So what we want to do is figure out how did they increase each one of these sides. But again, if we're talking about a storage box, what we have to remember is where that would be going in that box. So that we could go ahead and fold up the sides again and have everything work. So in number 43, what we'll do is we'll take some x value, and we're going to have to add the 5 that's already there. And then we're going to take some x value and add the 4 that's already there, and some x value and add the 3 that was already there. So similar to 39, but not exactly the same. We're still thinking about those 3 dimensions, but we don't have to put the 2x piece in here because this time this is going to be an increase. So basically what's happening is the box looked like this, and we're going to increase it by these x pieces to make this happen. So kind of a backwards way of doing it. And then it says, find the increase in each dimension. So what we want to do is use our calculator here. You could do some FOIL on this if you want to and get everything in one polynomial, but you could also just punch it in by subtracting the 120 from both sides. And then remember, our solutions are zeros. Our zeros will be what we see on the x-axis from those. And I'll go ahead and punch this one in for you. So we go back into the y equals on our calculator, and we had x plus 5, x plus 4, and x plus 3. And then we had to subtract 120. And I did have a box problem in here last time I was doing this one, so I'm just going to hit graph. No luck though, what I see here is I do see my 0, and that's all I need, but I didn't get to see the whole graph. So that's something we don't need to worry too much about, but if you wanted to, you could always tweak it so you can see it. but I want to know the 0. So what I'm doing is I'm bringing Blinky down here below the x-axis, and there comes Blinky now. So now I got Blinky. I want to make sure that he's below that 0 there, and well below. Got a y at -60. But I'll just press enter now, and then bring Blinky back up to where I could see him. And so there's our answer. It's just 1. X equals 1. So we could also get that one from the table. It's pretty rare that you can just get things from the table when you're working with word problems, but 1. We'd increase each dimension by 1. And that would be 1 foot in this case. All right. So a lot of integration with our technology in this section. This one says a rectangular box is 2x plus 3 units long, 2x minus 3 units wide, and 3x units high. What's its volume expressed as a polynomial? So this time we're not going to get a choice, and I'm going to call that v of x for volume. We are supposed to take 2x plus 3 times 2x minus 3 times 3x. And I wrote them down in order, but I would definitely keep that 3x out in front and then just quick do some FOIL with that difference of 2 squares pattern, the 2x plus 3 and the 2x minus 3. Because we really only have to do first times first. 2x times 2x is 4x squared. And last times last, which would be -9. And then multiply by our 3x. So 12x to the third minus 27x would be that polynomial. And you wouldn't have to use v of x, but you could use just f of x for function notation. But we definitely have to multiply that one out because it's said as a polynomial. Then number 47, we're finding the relative maximum, relative minimum, and zeros of each function. And I showed you how to do this on the graphing calculator with the others. So I'm just going to remind you that everything you need is up there at second trace. So give those a try now that I have done the others throughout the assignment. And then number 51 says, explain how the graph of a polynomial function can help you factor the polynomial. All right, 51, the graph will show the zeros. The zeros are factors. So zeros at A and B can be written as x minus A and x minus B. And that would definitely help you factor the polynomial to be able to do that. Then, for number 52, it says for each function, determine the zeros and state the multiplicity of any multiple zeros. So what we want to do is we want to pull an x out of this. And then notice that that's a difference of 2 squares pattern. So that's x plus 6 and x minus 6. So for this one, what we're going to want to do is just show that we have the 3 zeros and write down their multiplicities. And there we go. We have this one, which would be x equals 0, and that would have a multiplicity of 1 because it's to the first power. And then x equals -6 would have a multiplicity of 1 because we have those little imaginary ones sitting up there for those powers. And then x equals 6 also has a multiplicity of 1 because that's also to the first power. So remember, those powers help you out with the multiplicity. Then number 60 says, what is the polynomial function in factored form whose zeros are -2, 5, and 6, and whose leading coefficient is -2? Now I'm going to help you write this, but I'm going to leave it to you to go ahead and push this into your calculator here. If the zeros are at -2, 5, and 6, what we have to do is remember that that came from a factored form of x minus a. So that means originally it was x minus a -2, which would be x plus 2 in order to get -2 as a factor, x minus 5, and x minus 6. And then if they want a leading coefficient of -2, well, that's not going to happen with what we have right now, because this would be x times x times x, which will be x to the third. So all we're going to have to do is put a -2 in front of there to make sure that that happens. And it says graph the function and find any relative minimums or maximums. Again, I remind you, I did that earlier in the lesson, so I want you to give that a try.